Hello, my name is Adrien Louchet. I am a data center networking expert with Keysight Technologies. Today, I am at the Keysight Center of Expertise in Böblingen, Germany, to talk about the testing of the upcoming optical interface running at 100 gigabit per second over a single multimode fiber. Did you know that the vast majority of the transceiver installed in a data center have a multimode interface? They are deployed between the top of the rack and leaf switch, where most of the connections are, and when the distance is usually less than 100 meters. Currently, the industry is working on a 100G multimode interface to further decrease the cost, power consumption of the transported bits, but also to pave the way for the deployment of 800G in a data center. The 802.3db working group is following a similar approach for a 400G based SR8, which is based on 26 gigabaud PAM4. But the design margins are very tight at 53 gigabaud PAM4 because of the limited bandwidth of the VCSEL and because of the multimode propagation effects such as the modal dispersion. Especially, it is crucial to test the capability of a multimode receiver to accommodate from transceiver from different vendors running on different fibers. And for this, we need to generate a multimode signal whose key metrics such as TDECQ and extension ratio, as well as the impairment such as ISI or noise, can be accurately controlled. In order to do this, we can use the setup which is behind me. So this setup consists of a M8040 BIRD platform generating an electrical PAM signal up to 64 gigabaud. The M8045 pattern generators supports multiple sequences such as PRBS or SSPRQ or even FEC encoded scramble idle. Differential encoded can also be supported. It has 5 taps DN phases that enable to control the residual amount of ISI in the channel, and that can be used to embed or de-embed the channel. Different jitter types such as sinusoidal jitter, random jitter or budge can be injected into the signal. In addition, we have a M8054A interference source or an AWG that can be used to inject random noise and sinusoidal interference into the signal using a directional coupler here. The electrical signal is turned into an optical signal using a 81491A reference transmitter. Several options covering different speed and wavelengths are available. Here we use the 085 option for the 850 nanometer wavelengths. A special optical coupler is used to achieve an overfill Laund condition into the fiber. N7768 4-channel optical attenuator is used to condition the signal and control the power. Like his multimode switch counterpart, this attenuator is mode maintaining. That means that it does not modify the incoming mode distribution of the signal. And this is a key feature when testbeds include multimode fiber, because this ensures realistic multimode propagation effects such as mode coupling and modal dispersion. The signal is then captured using a N1092C sampling oscilloscope. This model has two 50 GHz electrical ports and one optical port with up to 40 GHz 3dB bandwidth. This scope can be configured to either emulate a reference receiver, that is with a specific receiver bandwidth and a digital equalizer, such as a TDECQ equalizer, or it can be configured to maximize signal fidelity by using the maximum bandwidth and reducing the noise. The capture signal is then analyzed in the Flex DCA software to carry out, for instance, jitter decomposition or compute metrics such as TDECQ, OMA, or extinction ratio. The N4917 BSCB optical receiver stress test can be used to generate the stress signal with the desired amount of ISI, interference, and jitter. The software retrieves the signal metrics computed by the Scope Flex DCA software and adjusts the equipment settings to calibrate the signal toward the desired stress mix and metrics. Here, for instance, we want to achieve a SECQ of 4.5 dB and have an initial ECCQ due to ISI of 3 dB. Such automation enables to reduce the time for calibration from hours to minutes. Here you can see an example of a clean 53 GBaud PAM4 multimode signal with a TD-ECQ below 2 dB and an extinction ratio above 5 dB. This signal is captured with a 28 GHz Nyquist filter, and the right eye diagram is the one which is computed by the TD-ECQ equalizer. After calibration, you can see that we have achieved a TD-ECQ of 4.2 dB for an outer extinction ratio of 3.6 dB. So I hope you found this short video interesting. Do not hesitate to reach out to me or to your KeySight representative if you have any question regarding this topic or regarding the feature solution. Thank you very much for your attention. Bye-bye.